Alright, so today we're going to look at dot products of vectors. And a dot product is just something that we use in other calculations. So if you have two vectors, to find the dot product, you're going to multiply their x values together to get one number. And then you're going to multiply their y values together to get a second product. And you're going to add those two products together and you get just a number. So the dot product is called a scalar answer because you don't actually get a vector from it. You get a number. And then we're going to use that dot product in some other things as we go along, and so we'll have one application of it today. And then we also have properties of dot products just like we had properties of vectors before, and some of them are the same. So I can multiply two vectors in whatever order I want to. Multiplication is commutative. However, if I have a scalar of 0 and I multiply it to a vector, I don't actually get a vector that's 0, 0. I get a scalar answer of 0. Because if you think about it, a vector that starts at 0 and then ends at 0, because that, if you had the component form of a vector 0, 0, that means it starts at 0 and 0, 0 and ends at 0, 0. Is it really a vector? It has no length to it, right? And then we can use the distributive property by taking a vector times the sum of two vectors. So we can multiply this vector to this vector, and then the u to the vector w, and then we can add those two vectors together. Actually, will this be a vector? What will the dot product give you? What's the dot product give you? A scalar number. So this is actually a number plus a number. So if I have the distributive property and I multiply a vector times the sum of two vectors, I'm not going to get a vector. I'm going to get a scalar answer. Having said that, I would personally find it easier to just add the two vectors together and then multiply by the other vector. The only reason why I might not do this is if I didn't have both vectors and maybe I was missing something in one of the vectors. Then we can have scalar, just a number out here that we're multiplying to the dot product. You can take that scalar number, it can be any number you can think of, other than 0. I guess you could use 0. What if it were 0? What would be your answer? What's 0 times any product? 0. So you can multiply the c to the u, but not to the v. In other words, you can only multiply that scalar number to one of the vectors, and then you multiply the vectors together. It's not like the distributive property where you multiply it here and here, because there's no addition sign in between. So all three of these things are being multiplied, so you can multiply them in whatever order you want to. You can multiply these together first and then times c, multiply the c to the u and then times v, or the u times the c times v. But you can't multiply that c to both of those. And then this last one is a vector times itself is the magnitude of that vector squared. And so I'm going to prove that to you in one of our examples that we do here shortly. What is the magnitude squared of a vector? How do you find the magnitude of a vector?
Just square it, find the magnitude and then square it.
Well, if I had a vector that has an x and a y, how do I find its magnitude? You square the x, square the y, and then do what? Add them together and take the square root. So if I squared all of that, what would you have? You'd have the x squared plus the y squared, right? So you wouldn't have any square root. So it'll be interesting to see, does a vector times a vector give you that same answer as the magnitude, but without the radical? That's really what it's saying. So we'll get to that in a minute. So let's just find dot products. Practice finding them. And if I were you, I would write out your notes, write them out in more detail than you normally would your homework. So to find the dot product, I'm going to take my x values, which are 4 times 2, plus I'm going to take my y values and multiply those together, 5 and 3, so 5 times 3, and 4 times 2 is 8, plus 5 times 3 is 15. What does that equal? 23. And so that just proves that a dot product gives you a number, not a vector. And so that's what that scalar answer means, because you got a number as an answer, not a vector. Then let's look at B. So we're going to do the same thing. I'm going to multiply my x's together. So I got 2 times 1 plus, always adding, our y's, negative 1 times 2. And I end up with 2 plus a negative 2. What does that equal? 0. Anytime you have a dot product of 0, the two vectors that created that dot product of 0 are very special. So these are going to be very special vectors you'll see later on. Anytime you have a dot product of 0, you'll go, aha, those vectors are, and we'll discuss what that is in a minute. I want you to find the dot product of C on your own without looking at my work. So you find the dot product on your own, and I'll quietly do mine up here. So when you get an answer, I want you to share it with those around you. See if they agree with you. Kylie, what'd you get? Did you all get negative 6? Perfect. So negative 6 is the correct answer. So that's easy, right? You're liking this chapter so far, aren't you? Wait till we hit polar coordinates. So next week, it'll all come to a screeching halt. All right, so let's use some properties associated with dot products. So we've got two vectors, u and v, and we're going to do various things with them. So for the first one, and you have to follow what they're asking you to do. So the first one, we're going to take u times v. So I'm going to find that dot product. So instead of writing everything out completely this time, I'm just going to shorten it up a little bit. 4 times 5 is 20, plus the product of my y's, 3 and 2, is 6. And what does that give you? Yep. So u times v is 26, scalar number, which is good. So then we're going to take that 26 and multiply it to v. So now we want to find what is 26 times v. So that would be 26 times the vector v, which is 5, 2. So we're just going to multiply the 26 straight in there. So I've got 26 times 5, comma, 26 times 2. Equals, what's 26 times 5?
30.
Yep, 130, comma, and then 26 times 2 is 52. Whoops, I don't want to open parentheses. It's not a dot product because we use scalar multiplication, so that's what we did in 6-1. I only get a dot product or a scalar answer if I multiply a vector times a vector. So in this case, I'm multiplying a number right here times a vector. And so you're essentially just distributing it into there. So we're just combining our rules from 6-1 along with 6-2. So try to keep those separate. All right, so then the next one, we're going to find 2u. So 2u, we're going to start with that first. So again, I have a scalar multiplication, 2 times my vector u, which is 4, 3. And so that equals 2 times 4 is 8, and 2 times 3 is 6. So then we're going to take that 2u and multiply it to v. So then we're going to take 8, 6, and multiply it to v, which is 5, 2. And so 8 times 5, my x's, is 40, plus my y's 6 times 5 or 6 times 2 is 12. And so I get an answer of 52. So this time I got a scalar answer.
Aren't you doing 2 times a vector and then a vector times that number?
Right, so 2 times the vector gives me a vector, right? And then a vector times a vector gives me a number.
Oh.
Just keeping that straight. And then for C, this time they want the magnitude of u. And so again, that's going back to 6, 1. So the magnitude of u is equal to the square root of the x of u is 4, and the y for u is 3. And so we get the square root of 16 plus 9, which is what? Which is 5. So that's our magnitude of u. And so then we're going to take that magnitude of u, which is 5, and we are going to subtract 3 from it for a final answer of 2. So let's kind of build on the fact that we just found the magnitude of u. So I want you to scroll back up here, and we're going to use this room right here to add a couple of problems. We're going to add 2 problems to that. And so the first problem that I want to add, it all pertains to example 2, so write small. Example 2, letter D. So remember I told you that I wanted to prove this to you? Well, maybe I won't prove. Yeah, let's prove this one to you. Right here. So what if I asked you this? The absolute value, or no, not the absolute value, there I go, the magnitude of u squared is equal to u times u. We're going to prove that. So we already know what the magnitude of u is. What's the magnitude of u? We found it in C, right? What's the magnitude of u? 5. And if I square it, what does that give me? 25. So we're going to find the dot product of u to itself, and it should come out to be 25, which means that you could find the dot product of a vector times itself 2 different ways. You could either just do it as a regular dot product, or you could take its magnitude and square it. Either way. And so let's take u times itself. So u is 4, 3. I'm going to multiply that to itself. So the x's, 4 times 4 is 16, plus the y's, 3 times 3 is 9. What does that give you? 25, which does indeed equal the magnitude squared. So it does equal the magnitude of u squared. All right, so then a little bit harder one. Example 2, letter E. So I want you to write the following. The dot product of W. I specifically chose W because we're not using the U or V from example 2. With itself is 6. Arnold, you're supposed to be writing this. What is the length? Of W. So to begin this problem, we need to write an equation to represent what the problem is saying. And the problem has said the dot product of W with itself is 6. So the dot product of W with itself is equal to 6. I don't know what vector W is. I have no idea what its coordinates are. But I do know that its dot product to itself is 6. I also know, based upon this theorem right here, this property right here, that the dot product to itself is also equal to the magnitude of that vector squared. So I could also say that W times W is equal to the magnitude of W squared. Wouldn't you agree? We just proved above here that it's true. So if that's true, I can make that conclusion as well. So if the dot product to itself is 6 and the dot product to itself is the magnitude squared, what can you conclude? Therefore, can't you put, say that again?
I said W times W.
No.
Magnitude of 6.
Can't I, if these are equal here, can't I set those equal to each other? These sides of the equation are both equal to the same thing, so you can set the 6 and the magnitude squared equal to each other. So therefore, the magnitude of W squared is equal to 6. If this is true, and this is true, by substitution, those must be equal. And so that's what I'm saying here. Now I can actually, and the question is asking me what's the length of W? Isn't the length the magnitude? Well, I don't want the magnitude squared. How do I get magnitude without that power? Yep, so take both sides though. So we're going to take the square root of both sides. And so we end up with the magnitude of W, which is its length, is equal to the square root of 6. So, therefore, the length of W is the square root of 6.
Is it just square root of 6 or is it like positive and negative square root?
That's a good question. So he wants to know, shouldn't it be positive or negative square root of 6? Because generally when we take the square root of both sides, we have to do plus or minus. But length is distance. And so distance cannot be negative. So that's why we're ignoring that negative. But it's a good thing to be thinking about. All right, so any questions on this front page before we go down to the very bottom? You good with all that? So let's apply some of it. So why do we learn all the dot products? Well, we're going to use it to find the angle between two vectors. So wouldn't you agree that if I have two vectors going in different directions, that there's an angle that's created between the two vectors? So we can find the angle that's created between the two vectors by using this formula, which was created by much smarter people than you or I. And so the cosine of that angle that we're finding is equal to the dot product of the two vectors divided by the product of their magnitudes. So if I can find the dot product and I can find their magnitudes, I can find the cosine of theta. But really what I want is theta. So what is theta equal to? The inverse cosine of that whole ratio, the dot product divided by the magnitude of u times the magnitude of v. So it's really what we're going to end up putting in our calculator. And that's when your calculator is going to come in handy. So let's find the angle. So for this one, I'm going to actually sketch my angle because both vectors are in quadrant 1. I'm just showing mostly quadrant 1. Be really careful when you partition this off that you partition it off evenly, as evenly as possible since we're not on graph paper. So I want you to have a good visual representation as well. So I'm going to let vector u be green, and it goes to 4, 3. So it's right about here. I'll just call this u. So there's my vector u. And then vector v I'm going to make blue. And so it goes to 3, 5, which is right about up here. So there's my vector v. So the angle that we're trying to find, there's our theta right there. So what makes this more difficult is if we were finding the angle from the x-axis to the green vector, you know how to do that because that's what we were doing in 6.1. Or if we were finding the angle from the x-axis to the blue vector, you can find that as well by using the inverse tangent, because we already know the coordinate points for x and y. And so what could you have done by using that knowledge? I could find the angle from here to the green vector, and I can find the angle from here to the blue vector by using the inverse tangent like we did in 6-1. What would you do with those two angles? You would subtract them to get that angle. So you could do it that way. Or this is less work. So let's go ahead and gather the information that we need for this particular problem. So I need the dot product, so write small. We're going to find the dot product first. So we're going to find u times v. So u times v is equal to, I'm going to take my x values and multiply them together. That gives me 12. Add to that my y values, multiply those together. I get 15. I think I said add previously, sorry. And then 12 and 15 is 27, right? So the dot product of the two vectors is 27. And the other two pieces I need are the magnitudes of the two vectors. So the second thing I'm going to find is the magnitude . So I'm going to find the magnitude of vector u. So we've been doing this a lot. So I'm going to square the x's, square the y's, and add them together. So my x's for u are 4 and 3, and my x is 4, my y is 3. And so that gives me the square root of 16 plus 9, which is what? 25, which we found before, right? So the magnitude of u is 5. And then step 3, we're going to find the magnitude of v. And so my x and y for v are 3 and 5. And so that gives me the square root of 9 plus 25, which is what?
36.
34. What divides into 34? 2, and it gives you 17. So is that simplified? Yeah, it can't be simplified. And so actually I'm going to put that in a different color. I'm going to put that in, because I'm going to color code everything. So this is going to be blue. And then I want my 5, I'll make it red.
I have a question.
Mm-hmm.
So you said u times u equal like the magnitude squared.
Correct.
So I multiplied u and u and then just took the square root of it, and you end up with like 4.
U times u would be 4 times 4 is 16, plus 3 times 3 is 9. That's 25.
16 times
And so the square root of that is 5 squared is 25. So it still gives you 25. Well, u times u. But the magnitude is 5. Because that to me is more complicated than just finding the dot product or the magnitude itself. Yes?
When you took the reverse cosine, why did you keep them? Why didn't we switch them?
Because you don't, when you do the inverse cosine, you don't take the reciprocal of the ratio. You take the ratio exactly as it is.
Is that always? Or
Mm-hmm.
just with us?
We've never flipped it.
Oh.
Never. Only if we were converting secant to cosine.
Oh, okay.
That's when we did that. Okay? All right, so any questions before we finish? Okay, so we've gathered all the pieces. So our last step is to actually find theta. So we're going to do the cosine of theta is equal to, my dot product is 27. So I'm putting in my purple 27. Divided by my two magnitudes, 5 times the square root of 34. Now, if I could reduce the 5 and the 27, I would. And if you can simplify this, you might. I mean, it's really not necessary to really do any of that, to be honest, because this is not a finished answer. We're really finding theta. So how am I finding theta? Yeah, so we're taking the inverse cosine of all of that, 27, divided by 5 rad 34. Now be really careful when you put this in your calculator. If I were you, I would figure this out first. And I would do 27 divided by parentheses 5 rad 34 and parentheses. Because otherwise, depending upon your calculator, you run the risk of dividing by 5, but multiplying by that rad 34 instead of dividing like you wanted to. So if you're doing it correctly, you'll get the following decimal for that ratio. You get approximately, and of course I don't want the approximated decimal, I'm going to use a whole decimal in my calculator. But that's what the 27 divided by 5 rad 34 should look like, 0.9261. Is there anybody that could not get that in your calculator? Because otherwise, when you go to hit second cosine and then second answer to put this in for the inverse cosine, you're going to have the wrong answer. So that's what we're doing next. So second cosine, second answer. And then you get for theta approximately 22.17 degrees. And it makes sense that the angle between those two vectors is a very small angle because it appears to be very small. So it seems a reasonable answer. If it came out negative, would that be reasonable? Nope. Not at all. Questions? All right, so we're going to go to the next page. So flip it. All right, so remember how I said that on this page right here that these were very special vectors, right? Look at page 2. Thank you. So we're going to look at orthogonal angles. I love that word orthogonal. And you have to know what it means. I'm going to ask you to give me the definition of orthogonal angles. And there's two parts of the definition. Part 1 says that if two vectors are orthogonal, then their dot product is 0. So that's part 1 of the definition, but it's not the end-all be-all. So I can tell if two vectors are orthogonal if that dot product turns out to be 0. So example 1, part B, those are orthogonal vectors. Well, what does orthogonal mean? The term orthogonal means perpendicular. So the vectors are perpendicular to each other. They have a right angle in between them. So if I were to use that previous formula, the cosine of theta is equal to the dot product divided by the product of the magnitudes, for those two vectors in example 1b, you should get 90 degrees for the angle. All right, so you have several questions in your homework where they ask you, determine if the two vectors are orthogonal. All you have to do is find the dot product. And so that's what we're going to do. We're going to find the dot product of those two which we've been doing all along today. So 2 times 6 is 12, plus negative 3 times 4 is negative 12. What's 12 plus negative 12? 0. So what does that tell you about the vectors? Yes, they are orthogonal. Why? Because their dot product is 0. What does that mean? The two vectors are perpendicular to each other. And if you were to actually plot those vectors out, so let's just look at them. We have a little bit of time. So I'm going to plot 2, negative 3. So I'm going to put that vector in green. So this is vector u. And then I'm going to plot the other one, which is 6, 4, which I'll have to go out a little further. So I'd be right about here. Granted, it's a rough sketch, and this is V. Do those vectors appear to be perpendicular? Does it appear to have a right angle there? Yes. Granted, I graphed it on non-graph paper, so we're off a smidge, but that's what they should look like, and sure enough, they do appear to be perpendicular. So, easy to tell, find their dot product. The other thing that you have to determine is, are two vectors parallel? Parallel vectors just mean that they are scalar multiples of each other. So you can either multiply one of the vectors by something to get the other vector, or divide one of the vectors by something to get to the other vector. And so if you look at these particular vectors here, can I multiply 3 by anything to get to 9? What? 3. That means I'd have to multiply the 2 by the very same thing, and it also multiplies by 3 to get 6. So if I had instead, like, let's say that was 3 and that was 9, but then this was 2 and this was 5, they would not be parallel because they were not both multiplied by the same number. So be careful with that. The easiest way to determine it is just to take the two vectors and place one of them on top of the other one and pretend like they're fractions and divide them out. So I'm just going to take 3 over 9 and compare it to 2 over 6. And I'm going to determine, are they equal? Well, in order to make the determination, you have to actually reduce them or show the cross products, either way. So I'm going to reduce them because I get 1/3 equals 1/3. So they do indeed check. They have the same scale factor, which is their scalar. So their scalar can be viewed as either 1/3 or 3, because it depends on which one you put on top of the other one. If I am going from this vector to this vector, it's a scalar multiple of 3. But if I'm going from this vector to this one, it's a scalar multiple of 1/3, because I'd really be dividing by 3. But the answer that they're looking for is yes. The vectors are parallel. And then you're going to love the last problem. We're not doing it. I don't find it useful for you. You're not going to use it in calculus next year. And you're not going to use it anymore this year. So we're not doing it. See? I do have a heart. Once in a while.